All right, so let's go to per unit analysis. And first of all, why per unit? Why do we want to do per unitization? What is per unitization? The first and foremost, basically reasons is that power systems have many interconnected voltage levels due to existence of power transformers, right? So you have power transformers all the way coming from medium voltage, going to low voltage or high voltage. All of these basically stages of transformation of voltage do exist in power systems. And usually we need to do the analysis on multiple levels of voltage in a given circuit. Okay, so one way to do that is to transform the voltage, current, and impedance levels whenever we go from one voltage level to the other voltage level, like the examples that we did last time. So if I want to, for example, do the analysis in this circuit, we found the IS. Once we found the IS, then we found IP from this MP over NS ratio. And we found ES. Once we found ES, we found EP again using this MP over NS ratio. So this transfer of voltage and current does need to happen whenever you go from one side to the other side. So this is an option that we have. But really, when the system becomes a complex system, you having many of these stages of voltages and currents, it's really hard, and we will make a lot of mistakes when transferring the voltages from one side to the other side, or the currents from one side to the other side. So therefore, a more systematic approach is required to do the analysis in these complex systems, and that's using the per unit analysis approach. So by doing the per unit analysis approach, we're going to, instead of using the units of voltage and current and ohms, we're going to use everything, all the numbers in per unit, which means that when the per unitization has happened on a consistent base level, it means that you should not worry about basically using the right unit of voltage, or transferring one current from one side to the other side, or transferring one voltage from one side to the other side. These will not be of your concern anymore. You just do the calculations using those per unit numbers, using KVL and KCL, and that's it. And once you have done your per unit analysis, you can take the numbers back to their actual or physical units. You can find out the voltage from per unit to its actual kV or voltage value, per unit current to its actual amps or k amps. So in a way, per unit analysis is kind of a normalization of your calculations. So when we say that, very simply speaking, when you have a transformer which has a 400 kV to 13.8 kV ratio of transformation, if you have a base, if the voltage over here, so remember this 400 kV, this 400 kV over 13.8 is kind of equivalent to the transformer's ratio, turns ratio. It doesn't mean that the voltage here, the voltage that you measure here, should be 400. It should be around 400, but it could be like 5% higher, 5% lower, anything in that range, or even more than that. When there are like things happening in the system, there is a lot of basically load in the system, the voltage could go even lower than 5% of its nominal value. So let's say if the voltage that you measure over here is 395 kV instead of 400 kV. Okay, so by doing the normalization, we mean that this 395 kV is how much in per unit? 395 over 400, that's is 0.9875 per unit. Okay, so this voltage per unit wise would be the same voltage that falls on the secondary as well. So, but on a different base. So if you just multiply this 0.9875 times, now the base on the secondary is 13.8 volts. This means that the actual voltage on the secondary side should be something around 13.6275. Yeah, so this is the per unit wise calculation that you're doing in here, but you could also do that using the turns ratio of the transformer. So let's say 400 over 13.8 would be the same as 395 over what? Voltage on the secondary side. So if you do the calculation this time using the transformer's ratios, 13.8 times 395 over 400, that is giving you the same value, right? That is giving you the same value. So per unitization, in very simple words, is something like this. So instead of using the transformer's ratios to do the transfer of voltage and current from one side to the other side, you do everything in using a systematic approach that you call it periodization. So how to perform the per unit analysis in a systematic way? We use or choose one arbitrary base value for the apparent power for the whole system. So you have a system, how complicated and big your system is. If it is like the system of under the territory of California ISO, okay, that big. You can take the whole base in terms of power to be, for example, 10 gigawatts or 10 gigavolt amps to be more accurate, because we're talking about apparent power. So choose that base, one base that is for the whole system. And this base could be arbitrary. You could take it to be anything. You could take it to be 1 watts. You could take it to be 1,000 gigavolt amps. You could take it to be 1 volt amps or 100,000 gigavolt amps or whatever value in between. It's completely in your hand, whatever value you want to pick. But it makes sense if you want to get good numbers that are not too big, not too small. It makes sense to choose that arbitrary base around the real expectations of power in that system. So if you have, for example, let me give you a more tangible example here. Let's say you have a generator, then it is connected to a transformer, then this is connected to a transmission line, then this is connected to a load. Okay, this is your power system. Let's say that this is 13.8 kV over 500 kV, and the transformer nameplates, the nameplates of the transformer in terms of power, that's also 500 MVA, just arbitrary numbers. So that MVA is the rated power. So for the transformer, you have a rated power of 500 MVA. You have a rated voltage of 13.8 over 400 kV. Okay, this is the nameplate of your transformer. Now for your generator, let's say your generator's nameplate is 425 MVA, and its voltage rating is 13.85 kilovolts. So you can see that, first of all, the devices that are connected to one another should have ratings that are comparable. So if you have like a 500 MVA transformer in here, it's a bad practice to connect it to a generator that has a 10 megawatt or 10 MVA basically rating. So you're not utilizing basically the equipment in a wise and optimized way. The devices that are connected to one another should all be around the same rating. So 500, I would say, is comparable to 425 MVA power-wise. Now, voltage-wise, the same thing. So if on the primary side, the transformer voltage rating is 13.8 kV, and so it makes sense to connect it to a transformer with, a generator that has a rating of 13.85 kV, okay? But it doesn't make sense. It is not a good practice to connect this transformer to a generator that has a voltage rating of, let's say, 2 kilovolts, right? Because these are not comparable to one another. So, talking about the same system, if you want to find out, rule number 1 in periodization was that you need to choose one arbitrary base value for the apparent power for this whole system. So I want to, although this arbitrary value could be any number, but it makes sense to choose a base of 500 MVA as the base, a space for the whole system, be 500 MVA. Or you can choose it to be 450 MVA. Okay, but it doesn't make sense to have the space to be, for example, 1 MVA. You get that? So the numbers that you choose, it's wiser to choose them around the common denominator, if that makes sense, of the whole system's of the whole equipment that do exist in that system. All right. And now you have to identify how many sections of, or how many voltage levels you have in your system. How many voltage levels do we have in this system? It's just 2. There is this side has 1 voltage level, and this whole side voltage level is 500 kV. So the voltages that you expect on this side of the system should be around 500 kV. The voltages on this side of the system should be around 13.8 kV. Now, you could go into more detail saying that, okay, this load is just a bulk load. So if you want to go further down and show this system more accurately, you might have another, for example, transformer step down, and then you have a load. And let's say if this is 13.8 over 500 kV, let's say this is the turns ratio on this side is 500 kV over, for example, 20 kV. Now, in this system, how many voltage levels you have, or how many zones of voltage you have? Three, right? So here is 13.8, here is 500, here is 20 kilovolts. Okay, now once you identify these voltage levels or zones of voltage, then starting from one side of your system, choose an arbitrary voltage base for that side. So this is side 1, side 2, side 3. It really is not important where you started from. So I can say that I start from side 1 and I choose the arbitrary voltage level, voltage base, V base in zone number 1. I choose it to be, for example, 14 kilovolts. Again, what value you choose it in here is arbitrary, but it does make sense to choose it in this around the same rating of voltage for the devices that are connected there. So it makes sense to choose it 14 kilovolt, but it wouldn't make sense to choose it to be 0.5 kilovolt, right? So this is not a good practice. Now, once you have chosen that V base in one side of your system and it is an arbitrary number, then you move around the rest of your system and the base voltage for the rest of the system would be determined or should be determined based on the turns ratios of the transformers as you are traveling through the rest of your system. Once I choose the voltage base inside 1 to be 14 kilovolts, then inside 2, what should be the voltage base? It should comply or should be consistent with the turns ratio of the transformer. So V base 1 over V base 2 should be the same as 13.8 over 500. So this means that once I chose V base 1 to be equal to 14, then V base 2 should be found from this. So V base 2 should be 500 times 14 over 13.8, or whatever value it's showing in, it's 507.25. Okay, so but if I had chosen instead of 14, if I had chosen 13.8, then what would have been the base of voltage of VB2? It would be just simply 500, right? So again, it makes sense. That's why I'm saying that choose the same ratings that are existing on the nameplate of your devices, because it results in less calculations. You didn't have to do this turns ratio calculation here anymore. If you had chosen the voltage base to be 13.8 on zone 1, and in zone 2, the voltage base 2 would be simply equal to 500. Okay? Now, because I chose it to be 13.8, I'll go back to what I had chosen. Now, can you tell me voltage base in zone 3? What should that be? So, correct. Or the other way around becomes VB3 over VB2 should be the same as 20 over 500, right? So from here, V base 3 should be found from V base 2 times 20 over 500. So whatever value found for V base 2, put it in here to find VB2, right? But again, if you had chosen the nameplate as the voltage base, you would have known that V base 1 would be 13.8, V base 2 would have been 500, V base 3 would have been simply 20 kilovolts, right? So you didn't need to do these calculations. So the key point is that the base voltages, when going from one voltage level to another voltage level, should change based on the turns ratio of the transformers that are used in that part of the system. Okay, so this means that I could have multiple voltage levels, voltage bases in my system. But for the whole system, I would have only one base for power. So one base for power, multiple bases for voltages. And then you could, once you have the base of power, and the base of voltage, you can find out the base of everything else in your system, every other type of quantity, which includes current, for example. Current is the one that we use a lot also. So what is the relationship between S base, V base, and I base? So S base would be square root of 3 times V base I base when you're having a three-phase system. Okay, so V base, usually speaking, in three-phase systems, you pick the base voltage to be the line-to-line voltage, the rated line-to-line voltage, and based on that, this relationship holds. If you have a single-phase system, S base would be just equal to I base V base, right? This is for the single-phase system. So from here, I base is found by S base over square root of 3 times V base. And from here, I base is found from S base over V base. Now, convert the physical units to per unit values by just dividing the physical units over the corresponding bases. So this is how you per unitize everything. So once you've done these, you've chosen these bases carefully, then the rest of the process would be easy. You just divide whatever value you have in physical units, divide it by its corresponding base, and you get the per unit value. Now, perform the analysis without worrying about the unit conversions anymore. Once you've done the per unitize everything, just use those per unit values. Don't worry about units anymore. Just use KVL, KCL, do the calculations. And then once you're done with your calculations, the values that you find are in per units. The results are in per units. You can always return them back to physical units using the same base system that you already have. Okay. Now, what happens to a transformer in per unit analysis? Transformers will be converted to nodes simply. Okay. So this ideal portion of your transformer would be nothing but, I mean, it's as if you just removed it. So IP would be equal to IS in per unit. IP, we know it's not equal to IS. The primary current is not the same as the secondary current, but when you per unitize your system, it will be equal in per unit. Okay, and then the impedances that you find in per unit, you don't worry about whether these impedances have been transferred to primary side or secondary side. Once you per unitize them, they're just per unit impedances in the transformer. They're not referred to any side. They're per unit values. Okay, so this means that if this transformer, the calculations in this transformer in the upper figure have been done in actual units, and we should have basically used RS, XS, VS, NP over NS, do the conversions to find, for example, IP from IS using NP over NS and so on and so forth. If you have per unitized everything, your system would have been converted into this system where everything is in per unit now. VS in per unit, XS is in per unit, RS is in per unit, everything else. I just put the per unit notation to show that they are the per unit values. And this ideal portion of the transformer has been also removed, and everything is done in per unit. Now, let's go over this simple example. So in this example, I have the physical values, RP 1 ohm, XP 2 ohm, RS 2 ohm, XS 4 ohm, NP over NS is 2. This is 1,000 ohms. This is a XM is 2,000, not 1,000, that's 100 ohms, and this is 200 ohms. Okay. I want to per unitize this system. So I choose an arbitrary power base of 8 MVA. Then I need to identify how many voltage zones I have, or how many voltage levels I have in my system. Because there is one single phase transformer, there are two sides. So there are two voltage levels. So typically speaking, each single phase transformer will bring two voltage levels into the equation. So I have side 1, side 2. Now, since I chose V base in side 1 to be 4 kilovolts, what does that mean for the voltage base on side 2? NP over NS. So the voltage on side 1 should be 2 times the voltage on side 2. The voltage on side 1 is 4 kV. So on side 2, it should be 2 kV. 4 kV over 2 kV is the same as 2. And then Z base on side 1 is just V base on side 1 over squared over S base, which is 2 ohms. V base on side 2 we just talked about. And then once you have this, Z base on side 2 can be found, which would be V base on side 2 over S base, which becomes 0.5 ohms. So I put the per unit values in here. And when I do not put units in a figure, it means that it's per unit by default. Okay. So just numbers. And these are basically the ratings or the bases that have been used for this per unitization. So we said that the reason we're doing per unit analysis is because when the power system gets complicated, there are many areas of voltage or many voltage levels that are existing when transformers are there in the system. So whenever a power transformer is there, there would be two different voltage levels on each two sides, on each side. So therefore, in order to basically do a seamless analysis without making any many mistakes while transferring the voltage and the current and impedances from one side to the other side, it's better to basically do the whole analysis in per unit on a common base of basically on a common base of consistent units. And then once we're done with per unit analysis, we can basically take all the units back to their physical actual units. Therefore, that's the main reason we're doing the performance. We're performing the per unit analysis. Okay, and to do that, we would choose an arbitrary base of apparent power for the whole system, but the bases of voltage need to vary when we're coming from one side of the transformer to the other side of the transformer, which means that we can start from one point in the system and then assume an arbitrary voltage base in that part of the system. And when we're traveling from that point to the other side of the system, whenever we reach a transformer, then the voltage base on the other side of the transformer should be changing proportional to the turns ratio of that transformer. So this means that we would need to basically consider the different areas in terms of the voltage or voltage levels. Like in this example, for example, there are two. There's a single phase transformer. Obviously, there's one side of side one, and there's side two. Each side has its own base. So if you choose the voltage base to be on side two, then the voltage base on side one would be determined based on the voltage base that you chose on side two, or the other way around. If you choose the voltage base on side one, then you have to change the side two's voltage base based on side one's basically voltage base and the turns ratio of the transformer. In this example, we had basically a transformer with two sides, and these were RP, XP, RC, XM, RS, XS, as well as NP over NS, which is the turns ratio of the transformer. These are given to us. And then we want to take the whole system to per unit using a common consistent set of basically bases. For that matter, we arbitrarily choose basically a space to be equal to 8 MVA, and we choose the voltage base on side one to be equal to 4 kilovolts. Okay, so once you change the system to per unit, we said that when we do per unit, each ideal transformer would be just one node. So this means that we practically remove this ideal transformer here and just put basically the magnetization impedance of the transformer, as well as the two series basically impedances on the primary and secondary. Now these need to be expressed in their per unit values. Okay, so this was how we're doing this. Now, because we're choosing the base on side one to be equal to 4 kilovolt, it means that on side two, the voltage base needs to be half of voltage base one, because it should be proportional. V base 2 over V base 1, V base 1 over V base 2 should be proportional to NP over NS. So because V base 1, we chose it to be 4 kilovolts, this means that V base 2 should be equal to 2 kilovolts. And then once we have the voltage bases and the S base or the power base, we can find out the Z base on each side. So Z base on side one becomes V base 1 squared over S base, and Z base 2 becomes V base 2 squared over S base, which means that Z base 1 becomes 2 ohms and Z base 2 becomes 0.5 ohms. And then based on this, we divide the impedances on each side divided by the Z base in their own side. So therefore, RP in per unit would be found from RP divided by Z base 1, but our S in per unit needs to be found from our S divided by Z base 2. And these are the numbers that we get after per unitization of the system.